Hello, and welcome to the Data Science Institute's virtual seminar series. My name is Dr. Leno da Silva, and I'm a Data Science Ambassador at the Lawrence Livermore National Laboratory. Data science is essential to many of the lab's key program areas. With the help of some of the world's most advanced supercomputers, we work in a variety of fields and application domains. Through basic and applied research, our data scientists are working to solve some of the world's most pressing challenges, in areas ranging from precision medicine and advanced manufacturing to energy and national security. Here at the lab, the Data Science Institute acts as a hub for data science activities, including this seminar series and other events to introduce new ideas and encourage collaboration. Speakers from other institutions are invited to share their innovative approaches with our data science community. With recordings of these seminars, like the one you are about to watch, we are reaching a wider audience than ever before. So, welcome. If you have questions or want to follow up after the presentation, check us out online at data-science.lbnl.gov or send us an email at dsi-seminars@lbnl.gov. Now, sit back, relax, and enjoy the seminar. Yeah, we have today Daniel Arnold here. He's a research scientist at the Berkeley National Lab and also adjunct professor of civil and environmental engineering at UC Berkeley. He graduated from UC Berkeley with a PhD in mechanical engineering in 2015 and was a postdoc at the Berkeley National Lab between 2016 and 2017. His interests are in the field of control theory, optimization, and machine learning. And his recent work mainly focuses on the use of those techniques for cybersecurity of electrical power systems. So, yeah, I'm going to give the word now to Dan, and I'm going to let him explain his work.
Okay, great.
Thank you for coming.
Thank you. Thanks, Leno. Am I coming through okay on, I can't see anybody, so am I coming through okay audio on the WebEx? I hope so. If I'm not, put it in the chat and I will figure it out. Okay, I see. Oh, I can see thumbs up. Oh, sweet. That's good. So there is some feedback happening. Awesome. Great. So thanks for having me here today. It's my pleasure to be able to give this talk. I'm Dan, and I'm from Berkeley Lab. The talk today is entitled Operational Cybersecurity of Distributed Energy Resources Using Optimization, Control Theory, Machine Learning. Let's break down the title a little bit. So operational cybersecurity. I like what's called the OT part of the power grid. So the physical things that move and make power go where it needs to go and protect the grid, regulate voltage and that sort of thing. I don't really deal with the IT side. I'm probably the last person you want to talk to about IT cybersecurity. I could not set up a firewall to protect really anything. And so I'll leave that to the IT folks. I'm more on the operational side. Distributed energy resources, we're going to talk about that. I'll define that term as we get into the talk, but this is one of the major paradigm shifts that's occurring now in the power grid, causing us to rethink a lot of the ways that we manage and control the system. And optimization, control theory, machine learning, these are my favorite set of techniques that I love to be able to draw on to address problems in the power system. And looking through the speaker list for past folks here, I'll probably not go into as much depth on those techniques because I think that's where the familiarity is with folks who are in the room or on the call. I'm going to spend probably more time outlining the threat vector we're looking at and how we approach addressing that threat vector using these techniques. So with that, we'll take it away. And interrupt me anytime. I'm used to talking to students; they can't control themselves. So just blurt out whatever you want to say, and we'll work it out. All right. So a little bit about me. Thanks to Leno for the introduction. So I'm a scientist at LBNL, and recently adjunct faculty in civil engineering at UC Berkeley, postdoc at Berkeley Lab before then. PhD, Cal, and before then spent some time in San Diego doing my master's and bachelor's degree. So I'm a mechanical engineer by trade. I'm not a computer scientist. So I really, at the start of my career, liked springs and dampers and heat transfer. That was pretty cool. And then I fell in love with control theory. And so that is the block on the lower right there. That's a block diagram of a simple search algorithm for a robot that I worked on during my master's program. And so control theory was kind of my gateway into optimization and machine learning, because you're really applying a lot of these techniques to systems that are just dynamic, which are a lot of fun. I spent some time after my master's working for the Navy on their underwater glider program, trying to get these devices to hold certain orientations so that whatever they were towing would be of use for the Navy. When I went back for my PhD, I wanted to work on the power grid. I knew that this was going to be a real important part of the energy transition. And then after PhD, joined Berkeley Lab. Very nice view sometimes when there's no fog on the hills there. And some of the things I work on at Berkeley Lab now are applying the techniques from adaptive control, from AI, machine learning, optimization for grid cybersecurity. And so this plot on the top there, that time series plot, is an example of what can happen if an adversary is able to attack certain resources in the power grid. You can create these oscillations in the grid. And some of the things that I work on are adjustments to other devices in the grid that we can deploy to try and make those oscillations go away. And so that's what, and we'll talk more about this explicitly in this talk coming up. So I thought I'd give you guys a little overview of the research we do for cybersecurity at LBNL. So we've been supporting DOE cybersecurity work since around 2012. Back then, the program was known as the Cybersecurity for Energy Delivery Systems program. It has since morphed into CSER. Cybersecurity, Energy Security, Emergency Response is the office that funds what we do now primarily. Our team competencies, we do a lot of, well, I bring to the table expertise in control theory, convex optimization, AI, ML, power systems expertise. My colleague, Sean Peisert, is an expert in computer security, differential privacy. So we have this really nice, I think, intersection of privacy, computer security, decision-making techniques, and then power systems expertise. And that's proven to be a nice mix so far. If I had to bin the work that we do into two buckets, I would say those two buckets would be using techniques from decision making, so AI, machine learning, control theory, for cybersecurity of the distribution grid, and then my colleague Sean leads projects that are really focused on data privacy, data sharing, so we can enable grid cybersecurity. CSER primarily. Yeah. We do work for the CEC as well, not as much. We do some work for the National Science Foundation, and Sean is pretty plugged into DHS and DoD, so he does some work for them as well. But what we're talking about here is primarily CSER funded. Okay. We have a lot of wonderful partners that we work with on these efforts. I'll be talking explicitly about NRECA in a few minutes. They are an organization that represents rural electric cooperatives, a very influential group, very important to address the needs of their constituents. We do have a lot of work with Cornell, some great contacts at Siemens, a variety of startups, including Kavala. We do work with the California Energy Commission, Portland General Electric. The list goes on, but these are some of the primary partners that we work with. All right, so getting into the talk here, it's broken up into 4 pieces. I'm going to talk about the rapidly evolving power grid and how that creates, and then that will lead into some of the unique cybersecurity challenges around distributed energy resources. I will define that term. I'll put a little bit more detail around that. And then I'll talk about 2 use cases, highlighting some of the past projects we've worked on, where we've deployed tools from algorithmic decision making. So that's what I would call like the umbrella on which I would cover control theory, optimization, artificial intelligence, machine learning, the science of making decisions, and how we use that for grid cybersecurity. And I'll talk about 2 use cases. One where we applied adaptive control for cybersecurity of the power grid, and then one where we utilize reinforcement learning and genetic algorithms also for cybersecurity of the power grid. And then I'll close with a brief discussion of some future challenges and opportunities, kind of what I see are some important work coming down the horizon that I think folks in this room would have the expertise to address. All right. So let's talk about a rapidly evolving power grid. It's probably no surprise to anybody who lives in California. Solar is everywhere, increasingly so. This graphic from the EIA shows just the the really stellar growth we've seen in solar electricity generation over the past few years, both utility scale and small scale solar. This list undoubtedly includes what are called concentrated solar generation, where you have big mirrors which focus the sun's energy, and you heat up some sort of working fluid, molten salts or whatever. But I think the bulk of this is largely photovoltaic generation systems. And so when I say photovoltaic or PV systems, what I mean are the flat panels that would be on somebody's house, or you may be driving not too far from here is Camp Parks. If you drive by Camp Parks, you see those big solar arrays. So that's what I'm talking about when I say solar mostly here. And you'll see me throw around this acronym PV. That's just shorthand for these flat photovoltaic panels that are in everybody's home. All right, and so the increase in solar generation, along with other kind of paradigm shifts occurring in electric vehicles and batteries, which I'll talk about on the next slide, is really changing the nature of the entire power grid. And so in the figure on the right, the power grid is broken down into three main sections that people often talk about. We have generation, transmission, and distribution systems. So generation historically was where the big spinning turbines would be located. These things are enormous. You burn coal or natural gas, you turn a turbine, you generate electricity. That electricity, that large amount of power is transmitted over long distances over the transmission system. You hit a substation, and then you step the voltage down where it can be utilized by folks in the distribution grid. Now, we historically had one-way power flow, where power generated from transmission, from generation would flow through transmission into distribution. But as this figure is showing here right now, generation sources are now popping up everywhere. We have some in the transmission system, in the generation system, and still, right, which are the large conventional power plants. We also have new players there: compressed air, hydrogen, batteries, pumped hydro, for instance. You have batteries and flywheels doing regulation services in the transmission grid. And where my focus is are all the tiny little generation sources in the distribution system. And so this is really a huge paradigm shift for the operators of the grid, because where we had to worry about one-way power flow in the past, now power is flowing in both directions. And that creates a lot of unique challenges there. Okay, I want to talk a little bit about the electric cooperatives, because this is a group that I feel is overlooked a lot when we talk about changes in the power system or addressing needs of folks in the power system. And so we're here in Livermore. If you live in this area, your power is provided by PG&E. PG&E is a huge entity. It's a big investor-owned utility, which has a lot more substantial financial resources than a lot of these electric cooperatives. These electric co-ops serve the most rural parts of the nation, and consistently some of the most porous parts of the nation as well. And so this entity, NRECA, is a lobbying organization that acts on behalf of the co-ops. And they're an excellent partner because they allow us insight into the challenges that's facing this really important community. And I wanted to explicitly incorporate this slide because some of the research directions that I'll talk about later in the talk were directly motivated by trying to make this technology more accessible for co-ops, because they don't have the financial resources and the staffing resources to really properly engage with a lot of this technology. So it's a good thing to keep in mind as we keep going. Okay, let's talk about this term that I had at the beginning of the talk, distributed energy resources. So when I say DER, what I really mean are sources of electricity generation in the distribution grid. So this can be your rooftop solar system. This can be your Tesla Powerwall battery. This can be your electric vehicle. If you have one of these, this could also be distributed wind. I haven't seen one, but I've heard they exist. If you talk to folks at Idaho, distributed nuclear is a thing. I haven't seen one around here. It's certainly not happening in Berkeley, but maybe one day. But the thing that's interesting about these devices is when a sunlight hits a solar panel, for instance, it creates electricity in what's called direct current. So those quantities are not oscillating. But if you look at your wall outlet and you were to take a sensor there and you were able to measure the voltage, you would see that that's an alternating current waveform. So it's fundamentally sinusoidal. And so we need some mechanism to reconcile direct current quantities being generated by DER, or being generated by DER through batteries, or V to G from vehicles or solar, and then to kind of turn that into alternating current quantities so that it can be exchanged with the power grid. And so the device that does that is called an inverter, and it sits. You can think of it as sitting in between the generation source and the grid, and it allows power to be exchanged between these two groups here. So these inverters are quote unquote smart because they have some intelligence that lets them do their job properly. The fundamental job of the inverter is to convert DC to AC so that we can exchange this power with the grid. But the power has to be conditioned properly, right? We actually care a lot about the quality of the power that we're going to be sending into the system. For those folks who do research in the power grid, you may know that the frequency of that oscillation is extremely important to maintain. That is a measurement of the health of the system, and we care a lot about what that value is. In addition to that, the phase of the waveforms, the relative phase, is really important because that essentially tells us how much power we're going to be transferring when we are going to be delivering power to the grid. And we have to care about matching the voltage as well, because if the voltage is too high or too low, you can get some very bad outcomes there. Devices could get burned up and sparks and all that not desirable stuff. And so these inverters, they have intelligence that let them properly condition the power coming in so that it can be delivered to the power grid. In addition to that, these inverters also have functions that allow them to support the grid if the grid is somewhat stressed. And it's these intelligent support functions that are going to form the primary basis of the threat vector that I'm going to talk about in this talk. All right, so let's get right into cybersecurity challenges associated with those smart functions. Okay, and so these functions are designed to do a variety of things. They will support voltage. They will support frequency. They will make sure that the quality of power being delivered by the individual DER is of a certain quality, for lack of a better word. And these control functions are being standardized by entities like IEEE, Rule 21, if you are familiar with what the CPUC has been doing in California. But these standards are outlining a structure for the functions that are going to be supporting the grid. And I have a picture of the title of the standard there on the left, and some examples of the function structure that dictates how inverters will respond to changing grid conditions are shown on the right. And so in the upper right, we have what's called the volt-var curve. This is a function that's going to change power injection as a function of the locally sensed grid voltage. So if the voltage drops too low, we're going to inject more power. If the voltage gets too high, we're going to curtail how much we're injecting. Because if you think about it, if the voltage is too high and we're going to add more power and we exceed some safety limit, then the things in the grid are not going to like that. There could be safety issues. It's in the interest of everyone, of the community, to curtail power injection and still be able to exchange some power with the grid, as opposed to overloading the grid and not being able to exchange any power. And so, and then in the lower section there on the right is a volt-watt curve, which also adjusts power injection as a function of grid voltage. And these functions are included now on solar installations, battery installations, which you could buy at your home. I got solar on my house from Enphase last year. These functions are included, and they're online and they're running, and they are in the system, helping out, which is fantastic. What's interesting about these functions is that there is not a one-size-fits-all kind of prescription for how these functions should be parameterized. In particular, the standard provides ranges in which these shapes can live, what shapes they can take. And so perhaps the homeowner, perhaps the utility, perhaps an aggregator has the ability to adjust these things. Okay, and the standard provides some guidance on how to do that. You would essentially be reassigning these different points in the 2D space to change the shape of these functions, and there's some regions in which these points can live. However, What's very interesting in the standard is if you read the footnotes, always read the footnotes. That's where the test questions come from. Always read the footnotes. It circled in the red there is an admission that if you don't do a good job of choosing what these functions are, you can get what's called grid instability, which is not good, and it really shows me that there is really a lack of complete understanding on the part of the folks who are putting these standards together in the community at large as to what these parameters should be. Okay, so there's a knowledge gap here that we can kind of fill, and in this ambiguity, there could be some issues with cybersecurity. All right, so why could there be issues here? These devices, it's probably unsurprising to you all, are IoT connected. There was a great example that occurred in Hawaii a few years ago. Hawaii, if you think about it, is the petri dish for solar in the US, right? We have a lot of solar in California. Hawaii is the California of California. So a few years ago, Hawaii had such a large deployment of solar devices that the utility, the grid operator in Hawaii worked with the vendor Enphase to adjust the behavior of the devices of their solar systems to make the grid more stable. And so HECO, working with Enphase, was able to roll out updates to 800,000 devices in a single day. Okay, so Enphase is a company that lives headquartered in Petaluma, not far from here. So somebody at Enphase pressed a button, and then 4/5 of all of the solar systems in Hawaii changed their behavior. And so, when I saw this, I was like, oh my gosh! So there are systems being put in place here where somebody can access these devices and fundamentally change how they interact with the grid. So these functions are great. This connectivity is great, but it's important to recognize that this is an expansion of the attack surface. Okay, so this is another mechanism that adversaries could utilize to potentially attack the grid, and we have to be conscious of that. And that is the motivation for the work I'm going to be talking about now. Okay, so just to put a pin in the threat model here. Okay, so all of these individual devices in a power system, right? Your rooftop solar system, my rooftop system, my battery, your battery, they've got these control functions. They are able to be updated remotely. And what we're talking about are an adversary making small adjustments to a lot of devices. And what's interesting about this is that if you were to monitor on an individual device by device basis, you may not think that a small change to one device could be a big deal. Okay, but it's the aggregate effect on the grid that we care about. If I change 100,000 devices by a very little amount, that's still a pretty big change for the power grid. And it's that attack on the aggregation of systems that we are interested in looking at. So what are some of the effects that can show up if an adversary were to take advantage of this? Well, you could introduce voltage oscillations into the system. This is an example of what a grid instability would look like. It's essentially these devices not able to find a stable operating point. They'll inject so much power, the voltage will go up. The control curve will say, this is too much. You got to curtail. They curtail power. The voltage is too low. Then they have to inject again. So they can't find a stable operating point there. Another type of attack we've looked at, which is also very interesting, are the creation of voltage imbalances. So power fundamentally flows on three phases, phases A, B, and C. The bigger customers get more phases. If you have a motor or a large industrial manufacturing, you are using three phases of power, and you care a lot about how far the voltages are from each other. Because if you don't, you can get damage to your equipment, your devices could trip offline, and it's a very interesting attack a very interesting threat vector to attack advanced manufacturing through that type of mechanism here. So these are two things that we don't want to see happening through attacks on DER. All right, so let me talk about now some use cases of past work we've done where we've tried to mitigate these issues here. Okay, and we're using the tools from algorithmic decision making. So if I had to pick one slide that I think is the most important for the whole deck, it's this slide here, which outlines the philosophy with which we approach control. Okay, so if you think about all of the devices in a grid, all of the DER, and you break them up into two groups, one group, let's say, is compromised. We can't do anything about that. We're assuming we're not going to be able to touch those devices. They're in the system. They have their behavior, which has been reset, and we're assuming we can't do anything about that. We're going to control the remaining set of devices. Things that have not been attacked, that have not been compromised, we're going to adjust their behavior using the same mechanisms that the adversary would use, using those grid control functions, and we're going to try and fight off the attack in real time. Okay. I think this is kind of what sets apart the work that we've done in the past, is that we're actively thinking about how we can utilize devices that are non-compromised in the grid in real time to mitigate what's happening with devices that have been maliciously adjusted. All right. Can I move this thing? I don't want my title to. Oh, I can. Look at that. Okay. So our control philosophy here. The idea behind what we're doing is reconfiguring the parameters in these control functions to fight off these attacks. And we do this through adjusting those points in 2D space on a lot of different devices. And what this ends up looking like when you think about it is we're taking these control curves, and sometimes we're moving them left and right on the x-axis. Sometimes we're stretching them up and down. We can compress them, and we can play with their shape in order to affect a response in the grid. And if we do this correctly, what we can end up happening is we have an attack that happens. We start to see some oscillations showing up from a destabilization. Our controllers will start to move the shape of devices we can control of their control functions, and then eventually we can mitigate the attack. And we've investigated a variety of different control paradigms because I think we don't really know if were we to go and deploy the solution, would it be something that a utility would, essentially be executing on the level of the entire grid? Like, would they collect all of the data, compute whatever control policy we need, and then roll out settings to the individual devices? And then we've investigated approaches that are designed to sit on individual devices, don't require communication, and would make adjustments locally to try and mitigate the attack. And so we've kind of looked at both of these. Oh, I need to click this now. Okay, so so thinking about attacks, these oscillation-based attacks, right, where the adversaries destabilize the feedback interconnection between the DER aggregation and the power grid. We utilized adaptive control as a defense against this type of attack. Adaptive control is really cool because what it essentially says is I'm going to gradually change things until I get the response that I want. And so you can think of it as trying to push a door open. If a door is kind of stuck, you're pushing on a little bit of force, it's not opening, you're going to push a little bit harder till it's going to give, and then you're going to be able to go through that door. And that's kind of what we're doing with the adaptive control here. And so with a fairly, I don't want to say simple, but modeling kind of the behavior of the solar system and the inverter at the timescales that we care about, which consists of these those control functions, which are that FP and FQ. Those are the nonlinear control functions in series with low-pass filters. We designed an adaptive control law, which is shown there on the right, which is just a couple derivatives and then an if-else statement. And we deployed this control law on individual solar inverters, and in simulation have shown that this is very effective in mitigating those type of oscillation attacks. There's a paper on it there if anybody's interested in reading up on this. DOE is also trying to patent this technology, so that's pretty cool. And let's see some simulation results here. So we have a distribution system, a rather large one from San Diego Gas and Electric. We took this model, we added time series of load behavior. So throughout the day, folks waking up, putting their kettles on, running their dishwashers. We added solar generation, batteries here, and added the dynamics and intelligence for how those solar devices' batteries are going to behave. And then we attacked the system. So we took a portion of the devices randomly throughout the network and adjusted their settings, and we created an instability there in the upper right. And then on the lower right, we've tested the same case, but now applying our control on the devices that have not been compromised. And so what's happening in the lower plot is once the instability shows up, our controllers detect this. we start to slowly change the settings and devices we control, and you can see that that attack gets mitigated in 150-ish seconds. And it's once it's gone, the voltage is acceptable, and business can resume.
Never seen data like this before.
Sure.
So I'm gonna ask a lot of
You
questions.
please do.
What time frame is this data that you got from this data from last year, last month?
Well, so
Sample.
sure. So the question was what time frame did this data come from? I'm guessing you're looking for how old this data is the question. Yeah. So the grid model. So this work is from 2021 or 2022. The grid model is the data we get from the utility, pretty much. Like that's when we approach a utility, that's typically what we're interested in getting. Is like, show me what your grid looks like, what that topology is. That's fairly static. That doesn't change too often. New devices are being added all the time, right? But in terms of the actual topology of the grid, where wires are connected, that doesn't change too often unless there's like an event of down power line or things like that. So this grid is probably still very representative of how that looks.
That's good.
Yeah. The data that we use to drive the simulation, so the load data, solar data, that is created from a tool that we have built that looks at statistical representations of solar and load data. So solar data, we can look at it from the specific geography. So we can actually generate data that's representative for San Diego solar there. For load data, there are geographic differences where you would care, like, am I in Texas versus New York? Because those loads are different. But by and large, those trends are not so different, where using data from one part of the country would invalidate the results if we were to use it like in San Diego. Please go ahead.
Well, I think you answered pretty much all the questions that were going to come up.
Go.
That.
Yes, that's the goal.
The data that you're working with has a long lifespan.
Yeah.
People agree that your approaches and the results are generalizable to their
Yes.
grid section.
Yes.
And then so maybe here's my relevant question. Do you have means of when I look at an image data set,
Sure.
I know more about, I do data augmentation.
Okay.
Is there equivalent things you do with this type of data to robustify your approaches, or is that not necessary given the quality of this data?
So I mean, I think the question is about robustness and generalization of this approach to, I'm guessing, the only thing I could think of where we need to generalize are other geographies, really. That would be the dimension that comes to mind right now. And it's not difficult to generate data that would be needed to repeat these experiments. A lot of the experiments that we have looked at have been actually not on specific geographies, but on these generalized test systems that IEEE gives us for experimentation. So we have every reason to believe that this technology would generalize sufficiently to other geographies in North America. Yeah, thank you. Great question. Okay, so attack defeated, point of this slide. Okay, so when we think about more sophisticated attacks, in particular that voltage imbalance attack, the technology that we built to mitigate the oscillation attack, which actually lived on individual devices, didn't require communication, it just kind of sits there waiting for the attack to happen and then takes action. That approach we felt was not going to be effective for looking at attacks across different phases of the system, because you require more data now. You actually need to know what's happening on the other phases of voltage in order to defeat those attacks. And so if we have a more sophisticated attack, we need a more sophisticated defense. And so we experimented with reinforcement learning for this problem. There are a lot of dynamics here. The dynamics are primarily inside the solar and battery inverters themselves. So it is appropriate to use a technique like this, we felt. For those who aren't familiar with reinforcement learning, people in this room I'm sure are. But how it fundamentally works is you have a decision maker who interacts with an environment through taking an action. That action is either good or bad and updates the state of the environment. And you feed this information, in terms of a reward, was this good or bad, and what the new states are, back to the agent, and then it learns if that action that it took was good or not. When in doing this work for this application, we are not trying to push the envelope on AI or reinforcement learning itself. We are taking stuff that's off the shelf and trying to tailor it so that it fits the solution that we need for this domain. And so 95 to 99% of what we did was in the environment block. So curating this simulation of the power grid with enough detail to represent the phenomena that we need to represent is where we spent most of our time. And once we had this environment, which consisted of OpenDSS, which is an off-the-shelf, popular power flow solver that a lot of utilities use to resolve power flow on their networks. Power flow, by the way, is a very nonlinear set of calculations that you have to run to see, okay, if I inject these powers at these parts of the grid, what are the voltages everywhere? What are the currents? So it's non-trivial to do that. But a lot of power flow solvers, they haven't had to in the past, so they don't have it now, represent the behavior of your solar system, your battery system sufficiently to model these attacks. And so we actually had to essentially augment what are these off-the-shelf power flow solvers with the intelligence needed so that we could use reinforcement learning here. So once we've built the environment correctly, then the actions become the updates to the parameters of the controllers in your solar and your battery system. And then the rewards and states become, so what were the voltages and power flow time series in the regions that we care about? And did you mitigate the attack or not? And so with that in mind, we were able to train agents to try and defeat these attacks. I want to say a little bit about what we thought was a pretty cool innovation for reducing the action space for this problem. If you think you have a grid, maybe there's 1,000 devices. They've all got their own control curves there. Each one has 4 points in 2D space you can move. That's a big action space. Okay, so that's something that we're thinking, well, do we really want to be making these adjustments to individual devices? So we did play around with that, but we found what is actually very effective is to simplify the action space by just constraining the dimensions to 1 dimension per device. And that's essentially how much we're going to translate these curves on the voltage axis. So we're sliding these curves left and right. And that's what the agent is going to tell us to do. And so we took the model of the solar system, the battery system we had before, which are just these nonlinear functions, nonlinear control functions in series with low-pass filters. And then we added some intelligence there, which is going to be and that's the neural network you see at the very bottom, which is going to be updating the settings of those nonlinear functions while sampling information from the grid, looking at past actions, getting a reward to see if it did a good job. There's a paper you guys can take a look at in ACC if you're interested in learning more.
Do you remember if the actions of the agent, they are allowed to be like the real number, or you just like discretize the field?
We played around with a variety of different architectures for the RL. So we looked at PPO, we did Q-learning. They were all fine. We had discretized action spaces, we had continuous action spaces. That didn't really change the nature of the problem too much. If you discretize, you just move in little chunks, and that was fine for us. Yeah. So I'll detail some experiments from one of the papers that I just shown. So this network topology is an IEEE test feeder provided by IEEE, the electrical engineering eggheads, who say this is a good feeder to represent something in North America. And so we took that feeder. We're doing what's called the unbalanced modeling. So we're modeling all 3 phases of power flow, which is a much more complicated set of power flow calculations there, but it's much more accurate, representative of real life. And then we added solar and battery resources there. And those are the circles. So those are normalized capacity of solar and batteries there. And then we said, okay, we looked at a variety of different approaches, right, where we attacked all on one part of the grid. We randomized the attacks. In this particular case I'm going to show here, the attack was equally distributed across all the nodes in the systems because why not? And so the red portion represents the amount of capacity at every node where there is a controllable resource that has been compromised. They have gotten bad settings. They're going to create imbalances. We're going to control the green resource, we're going to try and mitigate the attack. And so what's great about reinforcement learning is we were able to actually train it not only to mitigate the imbalance attacks, which is what the real goal was, we were also able to train it to mitigate the oscillation attacks simultaneously. So this thing is robust to either of these two attacks that can show up. It'll take action to mitigate that attack. This is an example of the agent applied to defend against the attacks that create voltage imbalances in the system. So on the left-hand side is the no defense case. That's the business as usual. So you can see when the attack occurs, there is a deviation, a separation of the voltages. That's in the top left subplot. The second subplot from the top on the left is the level of voltage imbalance in terms of percent. This is what the power system people care about. That's the metric that they don't want to see go above really 2%. 3% is actually pretty bad. Like that's motors shorting out and smoking, and so we don't want that. The third subplot from the top is the amount of action as a function of time that the agent has instructed the inverters to take, and then at the very bottom is power injection. And so you can see what happens on the right when we deploy this technology is that after the attack occurs, we actually squish the voltages back together. So we prevent that attack from being effective. And then when the attack is over, we return the voltages to their normal state of operation. So we release control, essentially. We reduce the level of imbalance back down to, it looks like just over 1%, which is acceptable. And then you can see the action that the agent has taken is actually non-uniform across the different phases of power flow. And so we're adjusting one phase more than another significantly at this particular location in the grid. And then you can also see what the power injections are doing at the very bottom.
This is a single node.
This is, I believe, the worst case at a given node in this. So of all the nodes, what's the worst? That's what we're showing here. Yeah. Good question. The question was, is that at a single node? And the answer is yes. So same agent deployed to mitigate an attack that creates oscillations in the system. Business as usual on the left. There's the attack, there are the oscillations. VO, the second subplot is the level of oscillations there. This is a metric that we actually came up with, which is a filtered version of the time series data that we feed the controller so that it understands oscillations are happening here. And then on the right, you can see the effect of the control where we're actually significantly reducing those oscillations in the system.
Can you give a quick summary of what VO is?
So, if you take the time series plot on the top, on the left, and you run it through a low pass filter, and you square that, and then high pass filter, square low pass filter. You're just extracting the energy of the oscillation. So it's essentially, think of it as the amplitude of the oscillation. Okay, so that's a great question, John. The question was, what is VO? I sprouted some math at John, which I shouldn't have done, and it's just the amplitude of the oscillation. All right. So effective in mitigating that attack. You can see that what action the agent took on the third subplot on the right, and then the power that was injected by the device at this node. All right. So briefly summarize the reinforcement learning aspect here. We used off-the-shelf reinforcement learning algorithms here. PPO, I think, was the most effective. Other policy gradient variants. We did some Q-learning too. That was okay. Q-learning was a little bit more annoying, as I recall, training, but it still worked. Nothing fancy on the AI on the ML side. Like the agents themselves are all just feed-forward neural networks. There was nothing more advanced happening there. That was more than enough to address this problem. One interesting takeaway that I'll share with you guys is that we found. And we didn't optimize this, so this could be pushed perhaps higher. But in our experiments, we found that our approaches were pretty effective when up to around 40% by capacity of devices were attacked. If we get beyond 40%, then there's just too many bad actors for us to do anything about that. However, we were always able to make the situation better. Okay, so even though we're not able to completely mitigate the attack, we can certainly reduce its severity. So I think that's a nice result there. The training time on what I'll call modest compute resources was like in the tens of hours. And this is mostly due to bottlenecks in the power flow simulation. So if we wanted to really knock this number down, we could spend some time there. However, I want to bring us back to the slide about the rural co-ops. In thinking about those as potential users of this technology. Is this approach suitable for them when we think about having to reconfigure the grid? Are they going to be able to retrain the system effectively? What if they have to retrain the system more often? Are they able to spend this time? And so basically, is this approach equitable to smaller utilities? And so in thinking about that, we tried to think of ways we could try and speed up the training process, which didn't require the huge investment of rewriting the power flow solver, which we didn't have the funding to do. And so this is where random search comes in. And so we experimented with some genetic algorithms to speed up the training time. So now we're stepping away from reinforcement learning, okay? And we're just going to be using random searches through rollouts of a given policy over an episode, which are like 10 minutes of simulation time. Not 10 minutes of real time, 10 minutes of simulated reality. And so random search, I love random search techniques because this brings me back to my master's degree in doing these search algorithms for mobile robots. These things are super cool. And so Ben Recht at Cal had a paper a few years ago on taking random search but making it a little bit better. Had some great results there. But what it fundamentally boils down to is approximating the gradient in a gradient update through rollouts of the policy in random directions. And so I'm gonna choose a way to update my policy. I'm gonna simulate that policy, and then I'm gonna do the opposite and get a simulation. I'm gonna calculate a gradient from that. And once I get these gradients, I can find the ones that perform the best, and then I'll update my policy according to those best performing directions. And if you do that, and if you're careful with how you choose your reward function, which is what I've shown here, in this case, the reward is the first term is I want to minimize the imbalance. That's VI. VO is I want to minimize that oscillation. The third term is I don't want to move too much from the last action. I don't want to be jerking the solar inverters around, going from full injection to full consumption. We don't want to do that. And there's a L2 regularization there. I don't want to have any of the control actions be too crazy. And then the last term is I don't want to curtail power injection if I don't have to. So I still provide value as much as I can to the homeowner, the owner of the device, so they can still sell their power to the grid. And we did this. We wrote a paper on it. So the paper was, let's take random search. Let's add atom instead of gradient descent. That's nothing fantastically new there, but we first to apply it to this application, we wrote a little paper on it. Okay. What we found is that we can reduce the training time by an order of magnitude compared to our previous implementation of PPO. I'm not trying to knock PPO. We did not exhaustively optimize the hyperparameters to let it do its best. But in terms of what we had already done, this was something that trains extraordinarily fast and is something that we felt we could, implement and package in a way that it would let these utilities of smaller financial and technical ability engage with the technology. All right, future challenges and opportunities. I am almost done. This is good timing. All right, so when I think about what the meta challenge is for utilities having to deal with this technology, there are a ton, okay? And I have one here, it's not exhaustive, but one thing that stands out in my mind is there are just so many buttons for them to push now, where before they had relatively few. So now utilities or aggregators, even if it's an aggregator utility, still has to kind of deal with it, but they have this new ability to control the power grid at the very edges of the grid, all right, through adjusting these parameters. So, and they can do this on every device. A home has, you may have a battery, electric car, and a solar inverter. So there's 3 things to adjust in your home. You may have a smart appliance. You may be doing demand response. You may have a smart thermostat. There are a lot of things, a lot of buttons that can be pressed. And I would argue, as evidenced by this table, which I loathe, that we don't understand what buttons should be pushed right now in order to keep the grid safe. And so I think that this is a real ripe area for AI machine learning to engage. It's a high dimensional action space, extremely high. But if we could take a crack at this problem, maybe we could give utilities a sense of like a sanity check. If somebody wants to come in, an aggregator perhaps, and says, I want to I want to bid these devices into the market, their ability to sell power. Here are the settings that I want to give them. Should a utility implement those settings? What is it going to do to their power grid? And so if they had like a lookup table where they could say this is good or bad, that would help them out a lot. And so we just wrapped up an internal lab LDRD, internal lab funded work, just scratching at this problem. Like, can we build a machine learning pipeline that is going to try and essentially predict if these sets of parameters are good or bad? That's all we want to do. And so through a combination of unsupervised, supervised learning, and some uncertainty sampling using Monte Carlo dropout, we built this kind of prototype pipeline where in a very simple simulation of a very simple power system where there's two dimensions that we're playing with, we can actually learn which parameters are good and bad. And so in this figure on the lower right there, it's 2D parameter space. Orange region is bad, blue is good. The dots are what our ML is predicting these parameters are going to be in that space. And we do a pretty good job of predicting blue on blue and red on orange. There's some better performance to be desired kind of around the borders. That's what I would expect. There's room to improve here, but I think it shows that this direction is promising, and we're going to try and look at some of our future projects. With that, I'll leave some contact information here. If you'd like to email me, I'd be happy to talk with you. Again, my name is Dan. There's my email address. My colleague Sean. If your questions are more on the computing sciences side, computer security, data privacy, please contact Sean. Our website is there. You can find out about some of our past work. We have some new projects starting in January, so there's going to be some new stuff happening on that website. But hop on there, have a look, and send me an email if you guys have any questions. John has his hands up.
So how, as far as scaling of reinforcement learning,
yeah,
basically how many nodes do you think?
So this is a question that we kind of wrestled with. We looked at feeders that were as large as like 1,000 nodes, right? So that's like a part of a city maybe. And we were experimenting with graph partitioning of the grids, and we were building a different reinforcement learning controller for like 1/10 of the size. So we'd have like one agent that would manage 100 nodes, one that would manage another 100 nodes, and that was pretty effective. Mm-hmm. And so I think I'm not sure how much that approach will scale. You may have to do multiple layers of segmentation and train the agents there. I think that's an important question. I'm not sure what the limit would be. That's a great question. Yes, we use the same metrics. Yes, we use. And what's going to be interesting? That's a great question. We may have to do some sort of aggregation as you go higher and higher, and that would be a very interesting research question to take on. Yeah. Great question.
So we have a question online from Maya. Is it possible to turn off compromised devices?
So we're assuming that we can't do that because if something has been compromised in the first place, we should not rely on it for control. Now, eventually, I would hope that those mechanisms would be in place to turn these things off. Big caveat to that, though. One thing I didn't talk about is one of the big challenges in the power system right now are stranded assets. So, for those of you who have solar installed on your homes, I bet a reasonable portion of you that that installer is out of business now. Okay, so you have a device on your roof that is generating power, and there's nobody doing maintenance on it. And so, is it unreasonable to think that these devices aren't going to be turned off? It's probably not. So, these stranded assets this is a big issue that we're wrestling with now in the power grid, especially now that we've changed kind of the rate structure in California for how we sell power. It's likely that more companies are going to go belly up, and so there are going to be devices that are not being patched, that are not being updated, that are still generating power, that are connected to the internet, and we have to learn to live with these things. And so turning them off would be a great, if I had that button, the kill switch, that would be awesome, and I would use it. We're assuming that that's not necessarily available to us. So good question. I hope that answers it.
Other question from the internet, from the internet. How is it that so many of these devices on the fringes are targeted simultaneously during an attack?
So when you think about how many vendors are out there that are creating the inverters themselves, there's really only a handful. So Enphase is very big. SolarEdge is very big. Siemens has some, right? And so there are probably, I mean, I can't say how many there are for sure, but I mean like a handful, right? Relatively small numbers. And if you think about what would probably happen during an attack, say Enphase's system gets compromised, this could happen. It could happen that Enphase and SolarEdge and Siemens all get compromised at the same time. Maybe there's a nation state who's executing that attack, but I think what is a likely scenario, what is certainly within the realm of possibilities, is one of those gets compromised. Enphase gets compromised. Okay, now their devices get bad settings, but the other ones don't. So you could reasonably have the situation where some of the devices are attacked all at the same time, and others are not. So here's a question. Great question from Tony. Oh, but it faded away before I could read it. Could you read that, Leno?
Yes.
It's lost to obscurity.
How do you distinguish from compromised device in order to fact reactive?
We don't make that distinction. We for the adaptive control, we don't make that distinction at all. The algorithm lives on the device. If it's compromised, we assume it's not going to be available for control. It's not going to do what we want it to do. If it's non-compromised, it is looking for the evidence of that oscillation. When it sees it, it adjusts its parameters. We don't tell it to do anything. It is a supervisory control that sits on top of the existing functions, and that's how it works. For the other devices, we assume that we have. For the other devices, we train the agent, or for the other attack, for the imbalance attack, we train the agent with random subsets of devices that have been compromised and non-compromised, and we deliver the same action to all of the solar or battery systems. So it ends up not mattering which devices. It ends up not mattering knowing which devices have been compromised or not. And this is the reason why those attacks kind of break down when you have too many devices that have. The reason why the defenses break down when you have above 40% roughly of devices compromised. Because we just don't have enough of devices available to recruit for control.
I have a question. So how localized are the observations that the devices have? Because like they are kind of like acting in a distributed way.
Yeah.
They're just like using their own observations.
Yeah.
How much of the like actual whole system can each of the devices see?
So it depends on which use case we're talking about. For the oscillation type attack, that was at the level of the device connecting to the grid. So that's like it's looking at the oscillations that are at the presence of your home, like at the voltage your home sees. So that's there. We looked at different aggregation points of mitigating the attacks for the voltage imbalances. Some of those were at certain select parts of the system, like maybe where there's a lot of branches coming out in the grid. And then we also looked at it where at the interconnection at the level of the home. And so that's just kind of a changing of the input mapping. So, I mean, if we wanted to retrain the agents to be sensitive to mitigating imbalances or oscillations at certain locations in the grid, we could certainly do that. But then you would not necessarily be guaranteeing that you're getting rid of the oscillations everywhere, right? If that makes sense. John.
So I'm thinking you train on 2 threads, and what if a third thread came in? Or maybe a simple way to look at it is you just train on one of the threads, that's the other thread.
Yeah. So we've looked at this too. We've looked at we train one agent for one attack, and then you have some metric that says, is this attack happening or this attack happening? And you turn on that control. That works fine. Actually, we had a student.
It's like say you train on one thread.
Yeah.
And then you don't know about the second.
So, okay. So this is cybersecurity, right? So like we're only limited by our imagination here. Yeah. And so when we started this project way back when, this is the culmination of like 6 years of work with DOE. We were told by DOE, because we wanted to do this, we wanted to build a system that would look for attacks different. And the DOE said, you are not to build an agent that attacks the power grid. And so they have since, I think, changed their mind about this, though, and are much more receptive to thinking about attack discovery. That is a huge open question right now, because what we did is we talked to NRECA and utilities and said, what do you guys care about in your systems that somebody would want to attack? And they're like, well, they could, drive the voltage too high, and then we have a ride-through event, right? You could create an imbalance, and we have to trip off these loads. You could create an oscillation, trip off these loads. So we're kind of driven by what the operators right now think are big issues. But there are, one of the things that's really interesting about this area is that the simulation tools we have are really, really bad. So the power system simulation tools are really, really, really lousy, and they don't capture a lot of really important phenomena that are showing up now because things are changing so fast. Like you have switches in these inverters that can go at like gigahertz, right? Really, really fast stuff. And so there's things that we're just not seeing. And so there could be some attack that is very impactful that we are just not considering right now. And that's really kind of scary. So yeah, thanks, John. Good to see you.
Another question from Hannah. For stabilizing the voltage, did you do any experiments based on the locations of the compromise or defensive?
Yeah. So we played around with like the attack happening at like one part of the system. All the attack is on the left, all the defense is on the right, and we looked at that. It really depends on the available resources you have, like how many are being. That's the bottom line. Like if the attack is too severe, you don't have enough control, you're not going to be able to do anything. But in that case, if you're very strategic with the devices you recruit for the defense, you can get away with fewer devices that you have to have that are executing more control to defeat very specific attacks. But I think you'd have to train agents that are specifically looking for that one attack, and that could be an overfit. That's what we're concerned about. Hope that answers your question.
Okay, last question. Through what kind of wireless technologies are these devices accessed?
Oh yeah, so I mean it's largely the internet. Cellular is also a popular power line carrier. I've seen that too, and so it's not always the internet, but recently that has been the primary mechanism through which these devices would be updated. I mean, like I have an N-phase inverter. I can go online and I can see what it's doing right now. I can see how much power it's producing, right? So these things are in contact. They can receive shutdown commands. They can receive updates for these settings from the vendor. What's very interesting is happening now with some recent orders from FERC, the Federal Energy Regulatory Commission. All these DER are going to be allowed to allowed to participate in electricity markets. And what that means is you're going to have this whole kind of cadre of new entities that are coming up. Startups are going to say, "Hey, I'm going to organize all the DER in this grid, and I'm going to bid into the market there." So you're going to see a lot more updates to these devices' behavior as part of that. And they're going to have to, and this has not been worked out yet, those aggregators are going to have to figure out how to work with utilities, because like what the utility does and what the aggregator does, like they're going to care about each other because they're using the same grid. And so it's going to be, I think, like the Wild West for a little while as we sort through, somebody wants to bid into the market and here are the settings you should have. Operator says, wait a minute, what's this going to do to my system? Let me double check. And so that there's going to be this really awkward thing happening for a little while. But that FERC order is going to change a lot of things. I think I went on a tangent there, but let me know if I missed the mark.
Okay, thank you very much. I think we are
awesome. Thank you. Thank you, Internet. Thank you, audience. I appreciate it. Thank you, guys.